Dear students, welcome to PHY 367 Statistical Physics 1. Today we will be learning about Lioville's theorem and ergodic hypothesis. Basically, this theorem deals with the density of points in phase space. So last time we learned about phase space and its different possibilities in classical mechanics and in quantum mechanics. And today we will deal with the continuity of the points in phase space. So for that we need to know or we need to recall our understanding about classical mechanics and classical Hamiltonian mechanics, I would say. So you have already learned about Hamiltonian formulation in classical mechanics. So it deals with the Hamiltonian of a system and its derivatives with respect to generalized momentum and generalized coordinate space. So from classical mechanics, we borrow the Hamiltonian formulation where Hamiltonian is a function of generalized coordinates and generalized momenta, and we know certain relationships about this Hamiltonian, that partial h over partial p is equal to the time derivative of the coordinate q dot or partial p q dt, and we have another relationship that is the derivative of Hamiltonian with respect to the space coordinate or space generalized coordinate, that is equal to minus p dot. So I call these two relations combined as our relationship 1. We will use this later. And now we are considering some set of points, and we relate those set of points to the density of phase space. So now consider a dense set of points in phase space in a certain phase space such that we are able to define the density function such that we have a density function rho, which is a function of generalized coordinates, generalized momenta, and time. And this thing, rho, which is a function of q, p, and t, q, dp, gives us the number of points with coordinates between q and q plus dq. So this is our definition of the density function that we actually I gave you this definition even the lecture before. So now consider equation 2. We call this equation 2. And now if rho is a function of q, p and t, so in terms of partial derivatives, we can write it as the derivative of this with respect to time. We can write it as partial rho over partial q times partial q over partial t plus partial rho over partial t times partial p over partial t, and then the last is an explicit function of time, so we write partial rho over partial t. We can put the values of, okay, first I write in this notation which I am using before, so that is partial q over partial t is actually q dot, and partial rho over partial p times this is now p dot, and plus partial rho over partial t, that you know very well. And now I can put the values of this q dot and p dot from our equation 1 here. So one is actually partial h over partial p, and the other one is minus times partial h over partial q. So we just insert these values. So we get d rho over dt equals partial rho over partial q times partial h over partial q partial t, sorry, minus partial rho over partial p times partial h over partial q plus partial rho over partial t. We call this our equation 3. Now if you remember that Hamiltonian formulation, then you know that this quantity here, this is basically a Poisson bracket between rho and h. So a Poisson bracket between rho and h can be written as partial rho over partial q times partial h over partial t minus partial rho over partial p times partial h over partial q. So we would just replace this thing here inside the equation 3, and we get d rho over dt equals rho h Poisson bracket plus partial rho over partial t. We call this our equation 4. Okay, so now we consider the phase space. You remember that a number of points or a number of accessible points in a phase space is a fixed number. So how many are the points inside some accessible phase space? So no new points can be created or destroyed. So there is a statement that number of points in a phase space is constant. What that means, that no new points can be created or no points can be destroyed. So no new points can be created and no previous points can be destroyed. So what that means is we can use the equation of continuity so we use the equation of continuity that we actually borrow from our electromagnetism. Equation of continuity, that is the surface derivative of J vector is equal to minus d over dt of the volume integral of the density, where J is the current density in that case. So the surface derivative of current density is equal to the time derivative of the volume charge density. So this we know from electromagnetism pretty well. I don't want to explain it here because we are not concerned with the derivation or anything of this theorem. But okay, we can somehow rearrange it. We can use another theorem. We can use Gauss theorem. Gauss divergence theorem. To convert this is the integral form of the relationship, and we now convert it into a differential form. So the differential form of exactly this equation is del dot rho v equals minus partial rho or partial t. So this del is now our generalized divergence operator. Del is generalized divergence operator, that is partial or partial q and partial or partial p, and this v is the velocity field in this case. V is the velocity field, that is q dot and p dot. It has two components, q dot and p dot, and this del operator has two components, partial or partial q and partial or partial p. And now we can just calculate this thing del dot rho v, the divergence of this thing. Okay, so when we converted it into, we can call this equation our equation 5 actually, so that we can use it later. So this is our equation 5 in principle, and now we want to calculate the left hand side of equation 5 using these two. So in simplified terms, it would be written as partial over partial q times rho q dot plus partial over partial p times rho q dot, and this would be equal to, okay, so we are now rewriting equation 5 basically. So okay, I write the right hand sides along this, so we don't have to rewrite everything again. So minus partial rho over partial t, and now we expand it. So use product rule. So q dot partial rho over partial q plus rho, if I take rho common now, so we will get partial over partial q times q dot plus partial over partial p dot and plus p dot partial rho over partial p equals minus partial rho over partial t. This is our next equation, our equation 6. So in equation 6, if you notice that I have separated out the term rho times partial of partial q dot and plus partial p. So this has very important significance. So what we do it, we just take this term out and we take partial over partial q dot and partial over partial p dot, and if we put now equation 1 in it, that is the definition of q dot and p dot, so it will become partial over partial q partial h over partial p minus partial over partial p times partial h over partial q. And since these terms are exactly same, so this term becomes equal to 0. So we can change the order of derivatives whatever we like, because this is an exact differential. So partial h over partial p and partial h over partial q can be interchanged, like the order of derivative can be changed because h is a exact, h has the exact differential form. So this is 0, and if we put it back in 6, so we get from 6 equation 6 implies that partial rho over partial q times q dot plus partial rho over partial p times, okay, I write this derivatives on the other side so it's not confusing. So from 6 we get this, and again if you put the value of q dot and p dot in this equation, we get, so this thing is again from 1, if you go back to 1 here, so q dot is partial h over partial p and p dot is partial h over partial q. So we write it partial h over partial p partial rho over partial q, and this is minus partial h over partial q and partial rho over partial p equals minus partial rho over partial t. So this is our Poisson bracket like this. So this is equal to now partial rho over partial t. We call this our equation 7. And now we want to put this equation 7 in our equation 3 here. So instead of partial rho over partial t, we put the value in equation 8, and this is again Poisson bracket, so 2 Poisson brackets, and they actually cancel each other out. Because there is a minus sign here, so that's why they will cancel each other out. So we write, put the value of partial rho or partial t in equation 3. So what we get t rho over equals 0, which means that rho is a constant. So this is the desired result we were looking for. This is called the Lioville's theorem. What does it say? It says that if a person moves along a point or along a set of points in density in phase space, the density of those points does not change with time. So I told you that if a point moves in a body moves in coordinate space, its corresponding point in density in phase space also moves. So now we take a collection of points, not single point but a number of points, and we say that these points are moving, like there is a shift of points in density space, in phase space. Then that means that after some time, if we saw that there is one set of points at one place, and later at some point we say they are at some other point space, the density of space will not change. What that means, I show you with some schematic diagram. So suppose we had initially this set of points in phase space initially, at time t is equal to t1. This is the situation at point time t is equal to t1, and later we have the situation that all these points have moved. So now they are here. But whatever their location may be on this phase space, their density, that is number of points per unit volume in phase space or per unit hypervolume in phase space, they will remain the same whatever happens at time t equals t2. This is somehow similar. This analogy is similar. This is similar or analogous to the movement of an incompressible fluid. If you have studied a little bit about fluid mechanics, so that will show you incompressible fluid. So a fluid, just like equation of continuity, so you have seen that whatever the density was up, it will be after some time it will change, and the height can be taken into account. But this is not about height here in case of the density of phase space points, but still it says that it moves like an incompressible liquid everywhere, whatever the next location might be of this density of this number of points, they will always remain the same. The number of points per unit volume will remain the same. We can also call this another, like we can express this fact in another way. So the Lioville theorem can also be stated as the Lioville's theorem can also be stated as rho, the Poisson bracket of rho and h should always be 0 for the system to be in equilibrium. So that also means that wherever we are applying our statistical mechanics techniques, if this condition is satisfied, that is the only way we can apply our conditions on that system. If this is not equal to 0, if rho and h Poisson bracket is not 0, I mean if rho and h do not commute, then we cannot apply our techniques of equilibrium statistical physics. That is the most important thing. We need to satisfy this condition before we can use it for equilibrium statistical mechanics. And I have mentioned it before and I am mentioning it again, that everything that we are studying in this course is dealing with equilibrium statistical mechanics. We are not studying in equilibrium or anything else, because that makes a totally different field. Everything we are studying in this course deals with equilibrium statistical mechanics. All these equations are valid for equilibrium statistical mechanics. That is, Lioville's theorem must hold to use these equations. The density of points should remain constant when the points move inside the phase space. And now we move on to the next topic of this lecture, that is the ergodic hypothesis. So for our ergodic hypothesis to be remembered, you should know that what a time average is. I mean, you know beforehand, I think. And this is a hypothesis, not a rule. So sometimes it is debatable how we can use it or not, but most of the time it fits our ergodic hypothesis. It says that if we have a statistical ensemble and we take ensemble average, if we have a statistical ensemble I mean a large number of similarly prepared systems, then this average, if we take and if we take average over all systems of a certain quantity, of a certain variable, we write this ensemble average as this. That can be written as the variable is a function of coordinate and momenta, and we have to average over density EQTP divided by the normalization factor. This is the similar to the expectation value or average value that we used to take when we studied probability. So that is the normalization factor, QP and DP. Then this average, ensemble average is what we call it, is the same as the time average of that variable. So how we take time average? So we measure that variable a number of times, like 10 times, 20 times, and then we note the time of that of all those measurements, and then we divide that the value of that variable with time, and that's what we call it as time average. So time average is, so ergodic hypothesis says that these two kinds of averages are the same. So first average is the ensemble average, second average is time average, which we write as sometimes we call it lab average. So that is F lab of that variable F, that is time taken to be for sufficient long time. Time t equals infinity, time t approaches infinity means we have taken those measurements for sufficient long time. It does not mean for t equal to infinity, but sufficient long time, so that the system is in equilibrium already. So the first condition is that system is in equilibrium. We have taken those measurements for sufficiently long time, and 1 over tau 0 to tau f of t dt. This is the time average formula normally we use, and this time average is equal to the ensemble average. So if we call the equation above as equation A, and call this equation, the lab average equation, as equation B, that says that according to ergodic hypothesis, equation A, the average taken via equation A equals averages taken via equation A are equal to averages taken via equation B. So this is actually very easy to understand. If you remember last lecture, I gave you a fundamental postulate of statistical mechanics. I told you that fundamental hypothesis of statistical mechanics that a system has all the accessible microstates equally probable. This was the statement of our. So a system has all the accessible microstates equally probable. This can be interpreted as a system spends equal time. This can be reformulated as the system spends equal amount of time in each accessible microstate. So now ergodic hypothesis is actually the equivalence of these two statements. The previous statement that we read or we know about, and this new statement that I am telling you, I mean the reformulation of that same statement. So if we have large number of microstates or accessible microstates in a system, then the system will spend equal amount of time in that each state. And a reformulation of that statement is that so these were equally probable according to one statement, and the reformulation is that that it spends equal amount of time. So if we now want to equate these two statements, then we have the ergodic hypothesis. So average is taken via the time average method, because now each state is equally probable. So for example, I draw another schematic diagram. So for example, this is our ensemble. This is totally schematic. It has no I should not draw any coordinates here. So assume that this is our ensemble with a number of states. So it is in phase space, so it has several boxes of equal size. This is the momentum axis, this is the space axis. So it has several boxes which are identical. Okay, assume they are identical. I have made maybe a little bit some big, some smaller. So assume that every of these boxes is similar. So now when our system moves, it spends some time here. Assume that it is moving in this direction, sometime in this, sometime in this, sometime in this, and then it takes this journey here, and then it moves back. So now because all the boxes are of the same length and width, and it spends equal time. This is the accessible phase space. Remember, this is accessible. So if we now take the time average, that okay, we measure all these boxes and then we divide it with time. Okay, measurements in all these boxes and then divide it with time. Then we get this time average. And now if we take the average over all boxes and ignore the time. Okay, so that for the time average we have to maybe consider the movement of this particle in actual space. Okay, so I draw it. So we have another space in which we have now the particle is moving in, say for example, coordinate space t and x, and then it has some random movements. Just like it moved here in phase space, it is moving somehow some random movements in coordinate space like this. So what we do, we take all these points here and then divide it with time, so we get some average velocity, for example here. So this average will be equal to this average. Actually this is a simplified example. There would be some other quantity, somehow complex quantity that we want to take average of, but for the sake of simplicity you can consider that this kind of average we are taking in lab. This is the average this is according to the equation B, and then this average is according to equation A, that ensemble average. So we count the number of boxes: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 boxes, and then we divide it with the normalization constant. Then we get this ensemble average, and this is the time average. And these two averages, according to the ergodic hypothesis, are the same. And you can take somehow some complex quantities and reach at the same conclusion. For example, if you take the case of tosses, the coin toss example, and you have the probability of getting some heads and some tails, and then you can do 100 tosses, or you can flip 100 coins together, and then the average you will get will resemble this ensemble average. And okay, then you can toss 10 coins daily for 7 days and then take another average, and that two averages will also be the same, the ensemble average and the time average. This is the general concept behind this ergodic hypothesis. But the equivalences of these two statements of the fundamental postulate of statistical mechanics, it has another outcome or another implication that I want to mention here. It says that in a closed statistical system, with fixed energy, all the accessible microstates have a constant probability density. So mathematically we can write it as rho is 1 over omega, where omega are the accessible microstates of the system, if the energy of the system is between E and E plus delta E. This 1 over omega is a constant, and it is 0 otherwise. This is also very important, and this is the case of fixed energy. This is true only if the system is isolated and it has a fixed energy. So I should mention, okay, so what is this? Omega is the total accessible microstates. So this will form a basis of our next main topic or next chapter, that is the microcanonical ensemble, in which we will study different systems under constant energy. But for those systems, this rule must be applied, that all the accessible microstates would have a constant probability density that is equal to 1 over omega, and it would be 0 if the energy is beyond these limits. If energy is either greater than these limits or smaller than these limits, so in those cases the probability density will go to 0. And this concludes our chapter, and next chapter we will be starting as of next week, and that would be microcanonical ensemble. I will assign you some problems for as exercises for this chapter. So till next week, bye bye.